Hey everyone, welcome and thanks so much for joining us today for this expert panel on dataset management using the right tools for the right job. My name is Russell Kaplan. I'm a director of engineering at Scale. I'm responsible for our AI infrastructure products. Today I'm joined here by Ariana Eisenstein, the CTO at Pickle Robot, Jack Guo, head of autonomy platform at Nuro, Louis Tremblay, AI ML engineering leader at Resideo, and Mostafa Rohaninejad, founding research scientist at Covariant. So for context on this panel, we've seen that AI in industry looks very different from AI in academia. And in industry, teams put a much larger focus on machine learning data sets, building the right data sets to build the right models. This is part of this increasing movement of data-centric AI. And so we've got an amazing panel here today of folks who are experts at their fields in many different aspects of this machine learning data set management problem. And so I would love to start out the conversation, Ariana, learning from you about how you build your data sets for machine learning in production.
Totally, and thank you for the introduction. We build our data sets through a combination of sources, both hand collected as well as capturing data from our production units in the field. We further augment this with sort of synthetic data generated from various sources, as well as sort of commercially available data sets that exist on the internet. We really sort of aim at a baseline for diversity, but we want to make sure that the data sets that we're building match our customer rollout plan. So we're very customer focused. We want to make sure that we're feeding our model training with data that really reflects the customers that we're serving in the near term, while building up data sets for those future reaching customers as we go forward.
Makes a bunch of sense. And could you talk more about, that sort of customer centricity? Oftentimes, different customers, different deployment environments, the data comes from a very different distribution. How do you focus on that when you're thinking about deployment? Can you mix all these different deployments? Do you have to build separate data sets for separate customers? And how do you sort of track that and improve that over time?
So this is this process is highly synchronized through our product development roadmap, where we rely on our product team to sort of build out a roadmap of customers that all sort of batch the kind of types of diversity that we see into a narrow set of criteria, where you can get a lot of visual variation at some levels that'll sort of maintain robustness across your sort of first wave of customers. But they all share similar characteristics for each sort of phase of deployment. We've found that the current market that we're addressing, there's enough need that we're able to really batch these deployments and add more diverse data sets into the model step by step, as opposed to having to maintain two separate data sets or multiple separate data sets for the varying levels of deployment.
Mostafa, you also have a lot of experience sort of deploying these ML applications in different environments. How is that similar or different from how you're approaching it at Covariant?
Yeah, thanks, Russell. And it was interesting hearing Ariana talk about it. I think there's a lot of parallels in our space. For the audience's background, like at Covariant, we're trying to build robots that can pick any objects in any warehouse. And as you can imagine, that's a very dynamic problem. There's a lot of variety, and obviously AI models are a good way of approaching that. Given the variety of models in our space, we actually have noticed we need a variety of different data streams, similar to how Ariana mentioned, to help train these models. I think most people, ML 101, you think of just like, supervised human labeled data, and that definitely is something that we do use. But that's only a part of how we feed our models. Another example, just as Ariana mentioned, is simulated data. A lot of these models either can't be, or they're dangerous to, or hard to be trained on real world data. So we really leverage simulated data and have tried to push as much as we can. As you can imagine, there's huge problems with like sim to real gap, and we really invested in our infrastructure to have as visually representative images as possible that can basically have these models transfer elegantly to the real world. We also have data streams coming from unsupervised data. So, I mean, that's kind of comes from two different categories. One is just real world data has structure. And like, say you have many images from a scene and you have calibration between them. That's just fundamental structure you can exploit. Also, when you're operating at a warehouse environment, you have free data. Like say there's like data coming about metadata about the objects you're picking. That's just like very like both interesting and almost infinite data that you can train on and help supervise your models with. We found that training almost all our models with some level of unsupervised data improves performance, and I think that matches the literature. And obviously, maybe the most clear one for a robotics application is experiential data, right? Like our robots have sensors, our robots interact with the scene, and based on those experiences, they need to improve. So that's probably the most important data source. Now, when you have these four different sources, you also have a variety of models that they feed into, and we have explicit hyperparameters around how much of each data stream goes into which model. Maybe there's different heads of models that are trained, say, unsupervised for one head, supervised for another. These are really architectural decisions that are made at like a model by model basis. And I think one last thing to kind of build on what Ariana was saying is when we have a variety of deployments, a lot of verticals, we really value having one model stack for all our deployments. I think that when you start going down the rabbit hole of having fine-tuned models for each thing or different stacks, like you're basically like are giving up on scaling. So it is hard. It's harder at the beginning, but you save time over the long run. So there's a lot of work on how we like balance between the data between different verticals and warehouses, so that we make sure that we maintain performance everywhere, but still have a universal set of models.
Yeah, I echo a lot of things that Mostafa said. So just to give a little bit of background, Nuro is building robotics applications, self-driving robots on the road to deliver groceries and better everyone's lives. So we adopt ML first strategy. A lot of the autonomy stack is learned, and depending on where those models are, like our data strategy could be a little bit different, but also fundamentally, like we have a fleet of vehicles that on the road that collects a lot of the data, and we have some mechanism to discover some interesting cases or hard cases from the vast amount of data that we collect. But then, if depending on the type of models, we have different strategy on the data set, right? For perception models, these type of problems are like very relatively easy to a human to annotate. So we have a lot of like human annotation efforts around it in collaboration with Scale AI. But for like prediction models, for example, you basically get free ground truth data by looking to the future. So we do a lot of auto labeling there. And for some of the reinforcement learning model, like similar to what Covariant did, like we use simulated data as a source for ML model training.
Louis, how do you think about those trade-offs in your application domain, right? I think like many other folks, you and the Resideo team will please share more context about what you're doing. The deployments can be in very different locations, potentially different customers, different environments. I think Mostafa's point of wanting to build one model and have it generalized across your deployments. I saw some vigorous head nodding. I mean, talk more about that, because there are a lot of trade-offs on both sides. How do you approach it at Resideo?
Yeah, so at Resideo, we're trying to make homes greener as well as homes safer. So that means security cameras and smart thermostats. And the application that I'm focused on these days is the security cameras. So that's doing good old-fashioned people package detection, animals, and trying to provide more insights to the homeowners to make sure that their homes feel safe. And of course, if we're deployed across the country, we're got all sorts of environments. And I'm sure Jack has similar domain issues where like you just get long tail problems that we're all kind of familiar with. And I kind of am jealous of a constraint environment of a warehouse that Ariana and Mostafa have. Well, it feels constrained to me in comparison. But I get asked all the time from product managers, hey, can't we just like train a model just on this specific home and then therefore like get really good performance on just that home and we won't get any false positives, or we'll be able to nail the business use case? And obviously the answer is yes, but that the trade-off to me is actually not so much in performance for the end customer, but it's actually the overhead that is associated for the engineering team to build that kind of large infrastructure that is required for that. And so as a leader in the org, you kind of have to always count your pennies in some ways, right? and like think like, well, is that really going to be the best thing that I need to accomplish right now for my problem? So I think proof of concept super important to get a generalized model, because it gets you that first wheel cranking and first feedback from the field. And then you can start thinking about the trade-offs of like, how much money do you really want to spend on like per deployment specificity?
Makes a lot of sense. One sort of idea or mode of development I've seen in some companies is to explicitly impose, sort of an amount of engineering time cap, you're willing to do on like your per cycle iteration, right? So like, hey, but if we want to upgrade our models, we're not going to spend any more than 1 week, or whatever unit of time it is. That includes the training time, maybe any customer specific customizations, and so everything's got to fit within that, just to kind of keep the rate of iteration high, knowing you might get better results if you spend more time, but that in aggregate, your reduced rate of iteration is probably or possibly more costly. So Lewis, I'm curious, at Resideo then, you do have all of these customers still at the end of the day. And as we know, a lot of these models, they're trained on large data sets, which means in some sense, the problems are more coupled than they used to be in the way we built engineering systems previously. So I'm curious, for evaluation of the models, how do you track those metrics, bias, data set drift, in an environment where you could be making aggregate improvements and helping things for some customers, but then regressing, for other customers? Ariana, Lewis, yeah, I'm curious for your thoughts.
I'll let Ariana go first.
Sure, thank you. Yeah, I take less time to train, perhaps not the perfect, or take less time and ship faster versus delay and ship at a lower cadence. We've certainly found in our space that it's highly detrimental to let perfect be the enemy of good, and that capping, time boxing is the word I always use with my team, your development time to here's what we can get done within this time period, leads to getting out into these deployments into production-like environments much more quickly. And certainly in the robotic space, Mostafa can probably echo this, your lab is never going to be as diverse, as complicated as your real world. And so leaving the lab as soon as possible is just huge. That being said, you want to make sure you don't take a production site down, you don't negatively impact your customers. So we sort of built, on top of sort of a traditional measure of our model's performance, a series of layered integration tests and validation tests prior to getting to the field, coupled with, a test site to your sort of small scale customers who are more tolerant of performance variation, I should say, before it goes to the broader fleet.
And building on that, exactly, I like what you said, how it'll affect the customer. And that's really what we end up focusing here at Resideo is not MAP or F-score, we look at those things for sure. But ultimately, what is the business case that we care about? In my case, was a package actually detected and dropped off? Yes or no, right? And having metrics that we're measuring against that is what I care about. And then in terms of marginal improvement against those metrics, then it's easier to make that business trade-off of like, okay, if I can go from 70% packages detection to 90% packages detection, that has a clear business impact that customers will be happy about. So yes, it'll be worth this amount of engineering dollars and so on. So we, just like Ariana, we have a framework where we're have this layer of kind of hard yes, no. Are we meeting the business case?
Yeah, that's really interesting, Lewis. I feel a lot of sentiments are shared, and a lot of your guys' experiences, I think we have co-learned. I think metrics are a problem that's super interesting. I think not enough people invest in it. I think that often you come out of school or academia and you're used to a world where your model is tied explicitly to a data set, and that data set has some metric, and all you're preoccupied with is optimizing the metric. So a lot of academics will really spend a lot of time on architectures and not on metrics. And I think that is a failing whenever you come into production. I think metrics are easier for some models than others. So let's use the example of supervised models. You have like, by the nature of like human labels, there is an explicit ground truth, and you can like, use the segmentation example. You have things like map, IOU, whatnot. Even at that simple level, I think those aren't perfect metrics, because in deployment, you don't really care about IOUs. If you tell your product manager I improved my IOU by 1 or something, he doesn't care. Like, what he cares about are downstream metrics like picks per hour, or mean time till human intervention, or number of wrong orders. So for just that example in particular, IOU is a symmetric metric. But like, for example, if you want to avoid double picks, you care more about intersection over precision, basically prediction. Basically, you're okay with like not having the mask cover the entire object, but you don't want to have the mask cover more than the object. And that asymmetry in the metric needs to be reflected in how you both train the model and how you evaluate project success. And that's just on supervised. When you start going to data that comes from experience, all that data is off policy. So now you're training up, your next grasping model or whatever. You're only evaluating it in an off policy way. Counterfactuals are nearly impossible. So to deal with that, you either need to have heuristics that you can get from the off policy data, or you need to develop model-based methods to basically make a simulator of what would happen in the counterfactual. We have invested so much in just simply getting metrics for other models, and I think more companies need to do that, because when you have metrics, it's like the classic thing, like you only can improve what you know or what you measure, and I think that's like a really important point for people to realize. And by counterfactual, like for example, say I have on some scene I grasp object A and it failed, right? I can't know if on object B somewhere else in that scene, if I did something, would it have worked or would it not worked? That sort of counterfactual is really hard to get from data that historical data, and that's where the model-based methods can help.
Yeah, I think, again, I echo a lot of things that Mostafa said. Is probably because our problem space are very similar. So in the autonomous driving space, I think there's two things that's different. Like, one is it's very safety critical, so you cannot really just push out the model out of the door and actually see how it works, because it has real life implications. And the second is similar to what Mostafa said. It's like the model metric is not the final metrics. You basically, what you care about is like you navigate safely on the road, or you are reasonably efficient in your trip towards the destination. So we actually have, in addition to the model side metrics that engineers iterate on, we also have some system level evaluation. This is probably similar to some of the system end-to-end integration that Ariana mentioned. From that process, we're able to get some signals on what works and what doesn't work, and be able to attribute that to, let's say, hey, this is actually a model recall problem of this specific model. And based on the failure cases that we discovered, we're able to maybe find more similar cases from the vast amount of data that we collect, and actually maybe incorporate them into the training data. So I think like the being safety critical and have a process that after the model training to be able to measure how effective the model is doing is basically something that's probably a little bit relatively unique to the robotic applications.
Makes a lot of sense. I think there's a fundamental tension in that a lot of these intermediary metrics we know are not the right long-term optimization, right? So your MAP or your object detector accuracy, this is obviously an intermediary value that hopefully provides some directionally correct signal of are you on the right track to make your models better. But often those end-to-end metrics, though they're more reliable, to your point, Mostafa and others, the end-to-end evaluation is just really hard when you have a new model, because you don't know all the counterfactuals of how does the real world react to how you behave, right? You don't know so many of the other variables, and sometimes they're also just computationally or time-wise much more expensive to compute. So I guess in practice, how do you deal with that disconnect? Do you tend to sort of discard intermediary metrics and really focus on end-to-end evaluation? How much iteration do you do based on intermediary metrics like model metrics, before you maybe run things through an end-to-end evaluation or a live evaluation? Any principles or sort of tips for the audience on how to think about that?
It's a great question. And And I think that tension is exactly reflected in my experience. I think there's a couple tips and tricks I can think of. One is, and this is a lot of work, but I think it's worthwhile work, is devise a semantic data set, a test data set. So for example, maybe I don't care about IOU as much, but I do care about double picks. So if I have a set of data that has ground truth like segmentation, and I propose grasps in like an integration test format or some sort of benchmarking, and that grasp would have been a double pick, well, that is clearly a case of segmentation failure that has downstream implications. So really having like semantically meaningful test data sets, I think is really useful. Another thing is like you can like devise metrics that are more precise for your application, right? I mentioned the example of intersection over prediction, right? So that really penalizes over prediction, but not under prediction. And there might be some more custom metrics that are specific to people's applications that can be more useful. And I think finally, I think that when you train models that can predict what happens in the world based on like previous data, then you can actually kind of like rerun, in our case, a pick, or and maybe rerun a ride in Jack's case or whatever, and that can be truthful to that what actually would happen in the real world. And that kind of offline pipeline is very powerful because, running stuff on robots in the real world can be expensive and dangerous if it doesn't go well.
I want to build on those. Those are all really great concrete things. But one of the things I've experienced really significantly is, Russell, to your question, like, are those metrics leading you in the right direction? Visualizing your metrics, and I don't mean like looking at a graph. I mean like actually looking how the inference result is and getting an actual intuitive sense of how your model is behaving kind of helps you guide those metrics and understanding like, okay, if that's a useful thing to keep following or not, right? Nothing's worse than just chasing a F1 score blindly and then realizing that you completely missed the use case inherently.
Yeah, I think that's a super important point as well. And in my experience doing machine learning, whenever the metrics and the anecdotes disagree, usually there's something wrong with the metrics. And there's just so many times where, the implementation is, training on the test set, or there's data leakage somewhere, or, the actual metric function has an error in how it's calculated. And then you wonder, hey, why is this end-to-end system, not working so well? But there's so many ways for errors to slip through kind of at each stage that aren't testable really, right? Until you evaluate things end to end and look at the examples. Makes a lot of sense. I guess building on that of, we want to use intermediary metrics to iterate faster, but we do need to evaluate things end to end, as much as we can. How frequently do you approach data set iteration? Is it kind of, hey, build a data set, train a model, then kind of keep tweaking the model? Is it more, hey, the data and the model should sort of co-evolve? We're constantly updating our data set, updating our models. How do you all approach this in your application domains?
Yeah, I can go with this. So from my experience, like we can actually decouple the improvements that's driven by data versus the improvement driven by the model architecture change. So from the data side, we have a continuous flow of interesting cases that flows in from our infrastructure, right? Like we have a vast fleet that collecting a lot of data, and some infrastructure to be able to query those data to find the interesting cases, especially the cases that the model doesn't do very well. Like for example, in the driver takeover, right? So those data are continuously flowing in, and from the infrastructure perspective, we want to be able to enable like retraining the model or fine-tuning the model on top of the new incremental data we get to be very easy, or maybe with some kind of like user supervision, right? Users say, hey, I want to get more data from this particular failure mode to find more interesting similar cases in this area. We want the user to be able to do that very quickly, and whenever like the user goes through this whole cycle, then we'll be able to deploy a new model. And there's like a separate type of effort where users are experimenting new architecture, in which case they basically want to do apple-to-apple comparison on the same data set with the new architecture. So yeah, there's like a couple of infrastructure work that to enable that. So I think the key thing to really make this process like really efficient is to look at the whole life cycle of the ML user workflow, right? All the way from mining for hard cases, get them labeled, irrespective whether that's like human labeled or auto label, preparing the data set, training, and post training model optimization and deployment to basically make this whole process as efficient as possible.
I want to build on that, which is the expectation of how quickly we iterate on data changes as the project matures. I'm actually in a scenario where I'm not just working on ADAS, I'm working on a whole bunch of different projects and different use cases. And at the very first get-go, maybe you get an iteration in 1 month cadence, right? You clean your data and so on, and it takes a month to go through. But at the moment that we're getting in front of customers or we have a life safety scenario like Jack, like it has to be quick. You have to it has to be seamless. So having a mindset of really robust ML ops right from the get-go and building that infrastructure in place is key.
Yeah, it's interesting to see how like domain-specific problems affect how we think about model iteration speed. I think as something that's specific to the factor use case is the deployment model for how we onboard customers. So just to walk you guys through that, often you sign a deal, some warehousing company, and you have a period from the moment you install the robot until what we call SAT, which is site acceptance tests. And that's a very finite amount of time. You want to minimize the amount of time solution engineers are on site. You really want to basically have as fast of a process from the robot, gets shipped there to the moment that it's handed off to the customer. So we really have a lot of pressure to improve whatever model needs to be improved in that period of time. So we try to invest as much as possible in that iteration speed. A couple tricks that we've come up with is some of our models are just continuously training. They never stop training. And they just kind of ingest data with every epoch. That allows for a couple things. One is you can, of course, have strategies around upsampling new data more or whatever, so that you kind of see that new data, say, quicker. And you can also just cut a release every day, every week, really up to you. So I think that's been helpful for us. And even having models that are more few shot oriented, right? So basically, if you can just train with a couple data points, obviously that's the fastest possible iteration speed. That can happen all on the robot station without having to go to the cloud and back.
Makes a bunch of sense. So on that topic, as these data sets are evolving, one of the key inputs is the actual hardware that's collecting them, right? For any of us doing computer vision in the physical world, which I believe all of you are, you can't decouple the data from how it's collected. And over time, you have different generations of robots, of cars, of cameras, of arms. How do you manage all that? And I guess, Ariana, would love to start with you here in your experience at Pickle Robot, because this is a challenge that we see very frequently in industries that, you've got a new generation of hardware coming online. Do you have to throw out the old data, recollect it? Is there a way to leverage that old data? How do you think about hardware upgrades for machine learning?
Totally. For me, this extends beyond the machine learning process in that anytime we start talking about a change in hardware, especially in the robotics space where your hardware and software are so tightly integrated and must always work together, we start with a pretty rigorous set of verification testing to make sure that this hardware upgrade is really what we need and delivering us the increase in input performance that we're really looking for. And we don't really take these sort of changes lightly in your hardware space to sort of upgrade your entire fleet, so to speak, with a new piece of hardware. Can be costly and expensive, but overall have a high impact. Specifically with respect to how do we, now that you've started to integrate this new piece of hardware, part of that validation testing is understanding in what ways your data set will either need to be augmented or altered in order to continue to keep your MLOps pipeline flowing as it was previously. With this respect, we try to work. So the first thing is, by design, work with as raw data as possible from all of these systems. minimizing any sort of pre-processing inputs that could just sort of manifest the model learning a piece of noise or like something that's vendor specific as opposed to raw data. In order to, and then we sort of leverage this delayed rollout to say, okay, if it really is the hardware change has required enough, has produced different enough outputs that we need to rebootstrap all of our models, we sort of take this opportunity to leverage pretty much all of the data streams at our disposal to kind of refeed the model to make sure that we can we have something that will perform at parity with our current best performing model, and then rebuild that as the new baseline going from there.
Louis, I imagine you have a lot of similar issues or challenges to overcome at Resideo, deploying hardware everywhere, all sorts of hardware, all sorts of upgrade cycles with all sorts of applications as well. How do you approach it?
It's actually by this is actually more of a soft recommendation, as in make sure you communicate to those teams with a cadence, and so that there's no changes that are unexpected. I have one anecdote where suddenly our models weren't performing very well on new data that was coming in. It wasn't clear. Turns out that the team had done a sensor change, just a one register sensor change, and suddenly there was a different amount of column noise coming through, and we just had to drop them in detection performance. Had we known that change early on, we could have augmented our training data and just kind of preemptively avoided an issue that became a raging fire afterwards. So I specifically, in this org and previous orgs, make sure that I have a monthly cadence where I'm talking to those hardware teams, the firmware team too. Nothing's worse than the firmware changing underneath you unexpectedly. That way you can kind of catch these things ahead of time.
Shifting gears a little bit, there are oftentimes particular challenges applying machine learning to a domain that only experts in that domain or people who have been serving real customers in that domain know about, right? There's challenges unique to package handling, to robotic pick and place, security, autonomous vehicles. Curious, what are maybe some of the trickiest challenges in your specific application domains, and how you overcome them, maybe relative to general machine learning problems?
I can probably share one example of some of the challenges that we encounter. So in autonomous driving application, because you want to provide redundancy and safety, so usually you leverage a lot of different sensors, right? Like camera, lidar, radar, or even for lidar, there's like long range lidar, near range lidar. So we need to synchronize those sensors in some way. So, and a kind of fundamental principle of the machine learning model training is we want to be able for the model to see the exactly same data at training time, inference time, right? So, but in our case, because there's so many different sensors and each sensor are triggering at different frequency, at different time, so there's not like a natural like synchronization point that just constitute like, hey, this is one training example, like some other application. So we need to be very careful about like how we synchronize our data at labeling time, at training time, and inference time. So some of the solutions that we have is to leverage leverage simulation framework to actually basically replay like all the data that would happen on board, and use that framework to prepare the data set. So to ensure the model sees the same data as the inference time.
Yeah, I think another challenge that comes from real world data is what I call like the health of the station or robot or system that collected the data. So just to give you an example in the robotic domain, let's say I have some calibration between my camera and robot, and for whatever reason the camera gets knocked and it's now slightly tilted. That really like spoils all the data that camera collects until you can update that calibration. Or let's say that I have a gripper and the gripper, accidentally hits something and becomes slightly bent. So in the camera space, it thinks that it's, going at the item head on, but it's actually an inch off. So for your perceptual model, it's like, no, this is a really good pick. But the output is like, no, you actually didn't seal on this object. So you really confuse the model. So something that we've noticed, both in terms of just keeping our robots running at the highest performance, but also making sure the data they're training on is valid, is having really rigorous station health metrics checking to make sure that the data coming in is always clean. Otherwise, it's really hard to rely on real world data because then it'll be so noisy and polluted that the models will be confused.
Super interesting classes of failures can arise from those types of challenges. Curious, Mostafa and others, what have been maybe some of the most interesting, unusual failures that you've dealt with in these machine learning systems, and how'd you fix them?
Maybe I could give one example and others should chime in. There's so many failure modes. It's really hard to you'd be surprised where objects can get jammed. You'd be surprised how the robot can injure itself. And I mean, there's just millions and millions of items that come and present themselves to a robot. So I think that basically having that interaction can cause issues with both the end effector and the robot itself, but also just say sometimes we deploy a station at a warehouse where it's 30 Celsius, and then during the summer it's 50 Celsius, and the actual aluminum frame of the sensors expand in a way that affects calibration. There's just such a variety of error modes. It's hard to pick one.
Variety, and also for the open world, the long tail problem is very real. I literally just last week had a false positive reported to me by my product manager saying, hey, it detected an animal in this video clip. And I take a look at it, and it was actually a bunch of kids dressed up in Halloween costumes, trying their Halloween costumes ahead of time. And is that a failure? How am I supposed to train a model that will, handle that situation gracefully? So that's definitely a challenge. And then on top of that, communicating that out to the customers is a big challenge, right? I had another one where a professional was getting a false positive off of a certain object that was in the front porch, and instead of kind of asking us and so on, he went and straight up replaced the camera with a whole new camera, thinking that would solve the issue, and unfortunately, actually did. So those are that has actually a real business impact. So odd failure cases long tail failure cases that have an actual business impact.
So many of those. And to me, that's honestly one of the fun things about working on machine learning is you're constantly surprised by what incredibly unusual, weird stuff does the real world throw at you that you could not possibly have imagined, guarding against. I remember when I was working on autonomous driving at Tesla as a perception engineer, we thought we had a good understanding of different types of failure cases for occlusions that could occur in the middle of the road. And we saw a clip of someone driving down the highway next to the divider, a truck coming across the divider on the other side with a bunch of logs stacked up in the back of the truck, hitting a bump, and the logs rolling out of the truck over the divider into the lane of motion. And that's the type of thing it's very hard to decide, we're going to run a sim test or synthetic data for in advance. But when you face it, you realize, this is going to be really hard. So maybe just on the general theme of what are the hard problems that we're facing and what are we facing going forward? One of the things that's exciting to me working in machine learning is that the field is moving so quickly. And so there's constantly new innovations. Mostafa had mentioned self-supervised learning being an important thing earlier. We're seeing a lot of improvements in leveraging simulation, improvements in metrics, synthetic data, et cetera. Curious what you all think. What's going to be really different building these production machine learning systems 5 years from now? And what's going to be the same?
So I'll jump in on this one. The thing that really excites me about building machine learning on these production systems is that as your product gets hardened and as it penetrates the field even further, being able to sort of pull out more of the, we sort of at Pickle Robot, we kind of see our system being built of a bunch of small learned components as opposed to one large model. And I'm very excited by using data capture and using kind of a better sort of filtering of these edge cases, seeing if we can pull more and more of our sort of tuned heuristics out of our system and replace them with smaller models that we can compose more intelligently, and then further pulling those out as our use case expands.
Yeah, I think what took me, I think I'm most excited about, and actually what brought me from academia focused, predominantly focused on academia to industry is, I feel like robotics in labs are fundamentally limited by the amount of data you have, because there's no business case for having thousands of robots in a lab. I think what excites me is the next couple years, there's going to be so many like production and business use cases for robots that we're going to have thousands of intelligent sensor-based robots in the real world, and we're going to have a lot of emergent properties that kind of come from learning on those vastly increasing sets of data. In the same way that like we have these super cool models trained on language and images from like the internet, I feel like there's going to be a similar phase of emergent properties coming from real world robotics, and I'm excited to be part of it.
Emerging phase, but also one thing that I'm personally very much looking forward to is for things to get simpler. I think we all have fairly complicated tech stacks to run this, right? And I think in the next 5 years, we'll see a merging of different tools, and things are just going to get a lot simpler for computer vision engineers to have an impact on their business use cases. And like, instead of customer expecting a several month project kickoff to get a POC going or something like that, to be able to do things really quickly and prove it to customers that we can have the impact that this technology has the potential to do is super exciting.
Some of the directions I see in autonomous driving or robotics fields in general are there are a few directions. Like one is of course, like more and more components will be learnable, right? Like previously, a lot of the components are like handcrafted heuristics, but now like we're basically to be more data driven. So the performance of the stack is driven by data, not by more and more engineers. So that I think will continue to happen in the next few years. And the second is just the scale of the data and the model. So as Mostafa mentioned, right, like in the large language model field, we've seen cases where if you increase the model capacity and increase the data set size you ingest, the model performance will improve, like basically logarithm in a logarithm space. So I think for the autonomous driving space, it will be very interesting to see how we can enable that to happen. I think we will have a lot of data, like for Nuro or maybe for a lot of other like business-oriented robotics companies. Like we have ways to collect a lot of data, but like how to leverage those data, how to train the large models effectively, leveraging all the signals that you have from the data is crucial. Like right now, maybe we do a lot of things by targeted data mining, but is there a way to automatically leverage the signal from a large amount of data is basically a challenge. And the third direction is probably more consolidation of the machine learning models, right? Like initially you have some parts of the stack to convert from heuristic based to learned, but then you end up with maybe a fragment, a bunch of models, and I think we're moving in the directions of more consolidated ML or like more end-to-end learned machine learning, in this space.
Totally agree. I think really insightful answers from all of you. For me, it's been fascinating to see, as you said, Jack, the scale. It just keeps getting bigger. And to your point, Mostafa, drawing the analogy to these large language models, there's these interesting scaling laws, right, that show, Jack, as you said, logarithmic performance improvements on your metrics that you care about as you get linear increases in data set size. What's also interesting to me about that line of research is often, the data set size, the compute you use to train the model, and the parameter counts of the model, they all have these scaling factors that, for sort of optimal efficiency, you have to grow in tandem. And even, for these large language models training on internet scale data, we're starting to approach limits first and foremost on the data set size front. And so I think when you take that insight and you apply it to what's happening in the physical world, just the amount of data we'll need to really kind of reach the potential of our modeling is enormous. So really excited for what's to come. And thank you all so much for joining us on this panel.
Thank you.
Thank you, Russell.
Thank you, Russell.
Thank you.
All right. Thanks all.